continuing to look at transformers, we're going to have a look at the difference between ideal and real transformers. And we'll start with an ideal transformer. It's a little bit easier. So in ideal transformers, we consider that there is no energy loss. So that means the amount of energy that we have going into the primary coil is equal to the amount of energy we have coming out of the secondary coil. In reality, that doesn't actually happen. There is no such thing as an ideal transformer. However, there are some transformers that are pretty close to being ideal, so there's very low energy losses. But we'll analyse this situation first. It's a little bit easier to analyse mathematically. We don't need to go into the mathematical analysis where energy losses do occur for real transformers. We'll just talk about what some of those losses are. But if we have an ideal transformer, that means that the output power, so the amount of energy per second, is equal to the input power. And if we look at power in this case, so the input power is going to be the peak voltage multiplied by the peak current in the primary coil, and the output power is going to be the peak voltage and the current in the secondary coil. So we can then look at the ratio there, so the input voltage over the input over the output, and compare that to the currents, and you'll notice that if we do that, we get this inverse relationship occurring. So Vp on Vs is equal to Is on Ip. And since power is constant in this case, given that it's an ideal transformer, if the potential difference increases, that means that the output current, so if the secondary potential difference has increased, the current will therefore decrease. So one of the important things about transformers is that as the voltage increases, so if it's a step-up transformer, the current will decrease. If it's a step-down transformer, the current will increase. So notice there that when we're talking about step-up and step-down, we're talking about the voltage, not the current. Now that leads us to the full equation that's in the data booklet. So we'll start out with what we've seen previously being the relationship between the EMF and the number of coils. If we then take that a step further, keeping in mind that EP over ES is the same as VP over VS, we then have a relationship to the currents that are produced, keeping in mind that for a current to be produced in the secondary coil, it must actually be connected to an external circuit. So if there's no circuit there, we don't get any current flowing. Now if we consider a real transformer, so as we said, an ideal transformer, there are no energy losses. In a real transformer, there are definitely energy losses, and we're just going to talk about what some of them are, and they can be minimized depending on which of the energy losses we're talking about, and these are due to a few different factors and a few different sort of design aspects of the transformer itself. So the first one that we need to consider is due to eddy currents in the core. Now eddy currents are basically if you've got flux being produced in the core, that's going to result in some sort of swirls of current in the core itself, and that the problem with that is that this leads to some heating of the core. And we're not talking about really ridiculous high temperatures or anything. We're just talking about that there is some heat that's being produced, and as a result some of the input energy is now being converted to forms that are no longer useful. The second one is flux leakage. A little bit of a funny sounding term there, but flux leakage basically results in the fact that while most of the magnetic field is produced in the core itself, some of it will actually sort of leak out the sides. So some of the flux leaks out the sides, and by leaks, what we really mean is that it's no longer going to be useful in generating an EMF in the secondary coil, and so as a result the flux that's being produced is not, well, the amount of energy that's being used to produce the flux is not being transferred through to the secondary coil. The third one that we'll look at is Joule heating. So that's the technical term. Basically it gets down to the fact that the wires in the coils have resistance. So resistance in the coils results in produces some heat as well. So in order to ensure that the Joule heating is as small as possible, you just need to make sure that you're using wires that have as low a resistance as possible. So they're the main causes of energy losses in real transformers. Last thing to look at with transformers then is, why are we actually using them? Why would we bother using transformers, and what's the significant purpose of them? And it basically comes down to power transmission. So when transmitting power, alternating current is used over direct current, and the main reason for that is that due to energy losses. And the energy losses that we're talking about deal with the current that's actually flowing. So let me just finish this sentence. So with if we look at DC, we'd actually have to have current flowing through wires, and so we'd have a high potential through to a low potential, current flows through, and we'd have a fairly high current, and as a result a fairly high energy loss. But with AC, at low voltages, so both for AC and DC I suppose, at low voltages, current in the power lines or transmission wires, so power lines being sort of the things that you'd see above the street, and transmission wires being sort of I guess those larger towers that you see in the countryside. So current in those is high, and that leads to and because those lines have a resistance, that leads to power losses. And the power loss is given by the equation, as we've seen before, P being equal to I squared R. So with high currents we have high power losses. So instead of using low voltage, we can use a transformer to step up the voltage. And as we've seen before, this decreases the current that's produced in the secondary coil, and as a result, if it's decreasing the current in the secondary coil, and they are also then going to be decreasing, that's going to decrease the current in the power lines as well, and as a result I squared R losses are also going to be decreased. So by stepping up the primary voltage to the secondary voltage, we decrease the current and as a result decrease the power losses. However, step-down transformers would then be needed to decrease that voltage back to an appropriate level for use in, say, homes and businesses. And one last little point to note here as well, I mentioned way back at the start looking at transformers, is that they come in different sizes and can be used at high powers and low powers. Most electronic devices don't actually require 240 volts that come out of the power point, and so you'll often find small step-down transformers that allow 240 volts to be then stepped down to whatever the voltage is needed for the device. So your tablet, for example, your power pack that you plug into the wall would have a small step-down transformer in it in order to provide the correct voltage to power your tablet.